We'll now take a look at intensity, which is defined as the rate of energy flow per unit area perpendicular to the direction of the wave. And in this case, the formula that we're going to discuss will apply for both transverse and longitudinal wave. So first, let's take a look at how intensity relates to the power and area. So as defined, intensity is power per unit area. So you take power divided by area. In terms of the area, if you're treating the source of the wave as omnidirectional, then we're looking at very much the area of a sphere. So in this case, the area of a sphere is going to be 4 pi r squared. So it will be P divided by 4 pi r squared. That's how we are able to derive the first equation, which is actually that the intensity is inversely proportional to r squared. The next one that we'll look at is we want to relate to the amplitude of the wave. Before we do that, we know that when the wave propagates through the particles actually oscillate in simple harmonic motion. So in simple harmonic motion, let us recap back the total energy stored in each of these particles, which is half m omega squared x naught squared. X naught squared is the amplitude of the transverse wave or the longitudinal wave. So therefore, because of this intensity, which is directly proportional to power, which is directly proportional to energy, is therefore directly proportional to amplitude squared. That's actually the second formula that we'll be using. So let us now take a look at polarization of transverse wave. First thing to note is that only transverse wave could actually be polarized because the oscillation of the particle is perpendicular to the direction of the energy transfer. If we now assume that the transverse wave is omnidirectional, if we assume an omnidirectional transverse wave that passes through this first Polaroid, where all the slits are orientated in this direction, then we know that only the transverse wave in this plane is able to pass through the slit. Those particles that are vibrating in this direction would actually not be able to pass through as physically they will be blocked, as physically the particles will be prevented from vibrating in this direction. Therefore, because of this, if we have an intensity of I naught that passes through the first Polaroid, then I1 will now be equal to I naught over 2. Because half the amount of the waves, half the amount of the particles that's vibrating in this direction would not be able to pass through the first Polaroid. However, in the case of a longitudinal wave, since the vibration of the particles is in the direction of the travel of the energy transfer, you can see that all of them could, in actual fact, passes through the slits, and hence because of this, longitudinal wave cannot be polarized, which is the reason why later the final equations that we derive will only be applicable for transverse wave. So now let us take a look at what happened after we pass through the first Polaroid, and say we place a second Polaroid and we rotate it clockwise by actually an angle theta. We want to study the intensity of the wave that has passed through the second Polaroid. So to do that, we need to analyze based on the amplitude. So earlier as explained, when we start off with an omnidirectional, source where particles could vibrate in this direction and this direction. After passing through the first Polaroid, the only particles vibrating in this direction passes through. So now if the particle is vibrating in this direction, but your slit is oriented in this direction, you realize that now the amplitude of the particles that could pass through is now A1 equal to A cos theta. This is actually the 90 degrees angle, and this angle is in actual fact a theta. So hence we can say that the I1, the intensity, is directly proportional to A squared, which is actually the amplitude of this wave, which is actually the amplitude here. Thereafter, and for I2, we can say it's directly proportional to the truncated or the reduced amplitude, which is actually A cos theta squared. By looking at this relationship, if we divide them, we'll be able to work out that I2 is equal to I1 cos squared theta. This is actually called the Malus Law, and it's something that we'll use only for transverse wave. The first two formula that we discussed earlier can be used for both transverse and longitudinal wave.